Good morning, everyone, and welcome to today's Life INDESAL webinar. It's a pleasure to have you all here as we explore innovations in sustainable seawater desalination. Today, we will dive into the latest advancements in circular desalination solutions, examining energy efficient technologies, resource recovery from brines, and how we move towards a truly circular water economy. We are honored to be joined by leading experts from academia, research, and industry who will share their insights and real world applications of these innovations. A special thank you to our distinguished speakers for their time and expertise. We encourage you all to engage, ask questions in the Q&A or the chat, and be part of the discussion. We would also like to inform you that this webinar is being recorded. With that said, I would like to pass the floor to our first speaker, Luca Spartella, project manager at Acciona Water Business.
Hello to everyone. Let's see if I can. Can you see the screen?
Yes, we can.
Perfect. So good morning to everyone. Thanks for being here to this Life INDESAL webinar. And my role is basically to introduce you to the Life INDESAL project, giving you some highlights of this project and what have been achieved so far. So I think in the context of today, most of us are very well known of the background of this and the need of a desalination project like the Life INDESAL due to the increased water demand and the water scarcity that we are facing in different regions of the world. And also, we know that there are several unconventional water resources that are becoming always more conventional, let's say. Among them, the desalination and seawater desalination is one of the most robust and efficient process to supply fresh water. In this framework, INDESAL aims to increase the seawater desalination sustainability and circularity. How we plan to do that? By integrating three different innovative technologies. So in this slide, we can have a brief overview of the project. There are 5 partners. Acciona is coordinating, and we are with our company, we are our friends, let's say, in this project, in this adventure, Apria, University of Cantabria, Redstack, and Revolve. The demonstration site is based in a southeast of Spain, in a desalination plant operated by Acciona, where the innovation department of Acciona Water Business has its own R&D facilities with several pilot plants, among them the Life INDESAL. So the main objective is to improve the efficiency and the circularity of seawater desalination with a novel integrated process. This process has, let's say, 3 pillars, which each of them is associated with a specific objectives, let's say. So the first pillar is to increase the energy efficiency of seawater desalination, and the technology is the low pressure multi-stage reverse osmosis. We will call it hereafter LMSRO. Then we want to generate renewable energies from brine with the reverse electrodialysis, RID, and transform brine into chemicals which are needed inside the desalination process itself with the electrodialysis with bipolar membrane, the EDBM. So from this technological scheme slide, you can see the 3 processes. So, and some of the main features related to them. So we have the LMSRO, which basically it's a 2-pass multi-stage with a shorter pressure vessels, which results in better flux distribution and also with a more flexible and tailored CIP, so cleaning place. The reverse electrodialysis can produce renewable energy in situ, and also we can have the advantage of having pressurized and pre-filtered inlets for this specific application. Finally, the ADBM, for which you can see also the simplified mechanism in the picture here in the top right side of the slide. We can have an in situ production of sodium hydroxide and hydrochloric acid to such extent which allows us to satisfy the requirement for the desalination process. So either for both, for the CAP and also for the pH adjustment. So these three technologies, which I have just mentioned, are integrated together in a pilot plant, which is highly flexible and modular, and basically it's composed by two containers, 140 feet and 120 feet containers, which are highly equipped and instrumented, and can be operated in such way which can be obtained, which allow us to obtain results representative for a full-scale desalination plant. If the first picture here we have at the top, we can see that our R&D facilities, and in the red dotted box below, we have like the INDESAL containers, let's say. In the bottom one, as we can see here in the right, we have the LMSRO. It's a 40 feet container, and the upper one, we have the other two processes, the RID and the DBM. So if we have a little bit more detailed look on the technological characteristic of each pilot plant, we we can focus on this slide in the characteristic of the LMSRO pilots. Basically, we have, like as I said before, two multi-stage two-pass system, and with an influent flow rate of 8 cubic meters per hour. And we also incorporate in our pilot an energy recovery device to have more reliable results in terms of scaling up process. Here in these pictures, you can see the interior of the red RID pilot plants with the stacks, which are two stacks manufactured by Redstack in a cross-flow configuration, and a variable flow rate, adjustable flow rate from 0.8 to 2 cubic meters per hour. Finally, as you can see, the picture of the inside view of the pilot is the same, because, as I said before, the RID and the DBM are allocated inside the same container. But in this case, we have also the detail of the DBM module, which in this case is a PC cell module with 10 triplets and influence flow rate of 300 liters per hour. So as we have seen, the highest flow rate is for the LMSRO, then the intermediate one is for the RID, and the lower one is for the DBM. Once we had a look on the technological characteristic of these three pilots, we can have a look on some of the results achieved. In the case of the LMSRO, we treat Mediterranean seawater, which is properly treated by the pretreatment of the pilot, so which is a pressurized media filters, which provides proper LMSRO influent quality with a turbidity and the SCD 15 complying with the characteristic that we need for proper LMSRO operation. And then, since we are in the Mediterranean, and actually in the south part of the Mediterranean, we have also we can reach high temperature in the inlet seawater. As we can see, it varies from 18 to 30 degrees Celsius in summertime. And this is an important parameter to evaluate, because it can affect the LMSRO operation. Anyhow, we can achieve from February, March till so the whole year, where the pilot was operated, we achieved like very good quality permate with an average of around 200 ppm of TDS. So looking at more proper results of the LMSRO system. So when we looked at the recovery, we achieved, we get 44% recovery of the force pass, which is a value highly representative of a full-scale system, which is usually operate between 40 and 45% recovery in the first pass. And then in the second pass, we have a lower recovery that would happen in the real life, let's say, but this is only due to pilot limitations because it was not possible to include more membrane inside the 40 feet container. But this is not a problem because then we can extrapolate the results and translate them to a process with more membrane modules, and we can anyhow use the obtained results at the pilot scale. So as I said before, we wanted also to give you some highlights regarding the highly balanced performance of the LMSRO. As you can see in the stage 1 and stage 2 of the first pass, we have almost the same flux in average. So these results in highly balanced and hydrodynamic conditions, and also with less energy losses. At the same time, we also were very satisfied with the performance of this force pass LMSRO, which presented a very stable performance. So once we have seen the LMSRO results, unfortunately, we cannot properly share continuous results from the other two technologies because at the moment they are not continuously operating. But it's anyhow interesting to see what some of the preliminary results at lab scale and also simulation, which were needed to achieve the final pilot plant design. So in the case of the RAD, Red Stack, which is the partner in charge of the design of these pilot units, due to their expertise in this in such systems, they have been like evaluating different process operation in terms of with the aim of maximizing to the possible extent the energy efficiency of the process, and of course the power density as well. These lab scale results were carried out in order to gain insights, valuable insights for the follow-up task, which is the construction and the design of the already pilot unit. And from this preliminary study, also together with the associated simulation, we built pilot plants flexible in terms of configuration mode, which indeed can be operated in a 2-stage and also in a single stage. This is why we saw from the preliminary simulation results that 2-stage configuration gave the best performance in terms of the energy yield which can be achieved, while the single stage process can be also useful if we want to restrict the low concentration outlet of the red process. At the same time, this pilot is also designed and built in order to operate in recirculation and feed and bleed mode for what it concerns the electrolyte rinse solution, because the idea of the project is also to achieve the maximum energy achieved with minimal or no chemical consumption at all. So finally, the RID pilots it has different and alternative operating modes. It also incorporates a novel smart control system for optimizing its performance, and we have an expected output of 1.5 watts per square meter. The similar context for the DBM. So in this case, University of Cantabria performed lab experiments and also simulation to design the pilot. And in this graph, we have the results from the lab experiments done with the same PC cell module, a smaller one but with exactly the same characteristics, where we wanted to see to which current density we were able to achieve the target of 3 molar concentration for sodium hydroxide. As you can see, the upper curve after around 600 minutes of operation, we're able to get to this 3 molar concentration. Since this process, this pilot is meant to be operated in a semi-batch way, we also have the advantage of operating at constant voltage, which in the case of the 850 amps per square meters, we are at around 20 volts of value. At University of Cantabria, also the effect of divalent ions, and as we see, their presence does not hinder the final concentration achieved. But yes, as most of us here know, the divalent ions results in higher resistance in the process, therefore higher energy consumption. This is why the pilot also includes a nanofiltration pretreatment. So finally, the EDBM can operate in semi-batch mode. The idea is to start with an initial concentration of 0.5 to achieve a target 3 molar concentration, mostly for sodium hydroxide, and a production of 86 grams per hour of the alkaline stream. So getting to the conclusion and some of the expected results from the pilot plant operation, we expect a specific energy consumption reduction of 0.2 kilowatt hours per cubic meters when we compare the LMSRO system with a conventional 2-pass seawater reverse osmosis desalination system. We expect to achieve up 0.1 kilowatt hours per cubic meter of permeate of renewable energy due to the RID, and to satisfy it completely the need of sodium hydroxide and hydrochloric acid for the proper operation of the pilot, thanks the ADBM process. Then if we translate these results to a full-scale desalination plant, we will have a reduction of 33 gigawatt hours per year of and the associated reduction of CO2 equivalent emissions, the production of 16 gigawatt hours per year, and a reduction of 4,000 and almost 200 tons per year of chemical due to the brine valorization due to the EDBM process. So finally, I would like to thank all the actors involved in this works done so far. Also the audience presence here. I see 82 participants, so thanks for being here today. And mostly thanks to the following keynote speakers for being here with us and showing us their interesting research. Thanks a lot.
Thank you, Luca. Now I would like to pass the floor to Jorge Juan Malfeito, Director of Innovation Department, Acciona Water Business, who will present evolution of RO seawater desalination technology.
Good morning, everyone. Thank you for coming to listen our webinar. And in particular, my presentation is going about evolution of RO seawater desalination technology. First of all, don't panic. I'm not going back to the time of the ancient Greeks, despite my first slide. But only I would like to remark that the salted water is some of the issues along the whole humanity history. Of course, the main technology is different stages of distillation processes, from the lower scale for villages, boats, etc., to the full scale that appears in the year 1930 in South Arabia, in which the first big multi-effect desalination plant was built. Following that, in the meaning, the United States Congress passed the Saline Water Act to support the funding of desalination in 1952. And in Qatar, the first desalination plant was in 1954. And what happens in early 60s, last century? So in the University of Los Angeles, Sidney Loeb and Srivanan Surirajan discovered that cellulose acetate film can separate salts. They find initially by casualty, they find that the cellulose acetate film that covers the packets, the cigarette package, can separate salts. And later on, they start to investigate the cellulose acetate that support the films in that it was made by cellulose acetate, of course, and they start to testing different ways to build these films until they reach a more or less commercial cellulose acetate membrane, with enough flow, enough salt rejection to become into a commercial, start to commercialize this kind of membranes. The second step was the discovering the invention of the spiral wound elements, did by Brine in late 60s. In the picture, you can see the first spiral wound element for lab scale in 1963. In the picture, you can see the first bigger scale prototype made by Brine. But the breakthrough in this technology was the patent by Cadot, the so-called 344, in which established the standard for manufacturing the interfacially synthesized reverse osmosis membrane, which is basically the chemistry that all the reverse osmosis membranes manufactured in those now actually. This process is a chemical reaction between an diamine, aromatic diamine, and aromatic diacid chloride that form an polyamide, cross-linked polyamide, very, very thin, only 0.2, 0.5 microns thickness. But this very, very thin layer is responsible for the properties of the whole reverse osmosis membrane, responsible for the salt passage and responsible for the water flux. In 1961, President Kennedy signed the Saline Water Conversion Program in the United States, and for all these facts become in an actual reverse osmosis desalination technology. The first desalination plant by reverse osmosis was in Lanzarote in Canary Islands in 1964, following by the Israelis' first desalination plant in 1965. And in Spain, the first desalination plant for meat irrigation demands was in 1987, also in Canary Islands. In Israel, in 1997, in Israel, Israeli government started the master plan, desalination master plan for irrigation, and in Spain in 2004, 2005, they started the AGUA program, in which we built more than 24 seawater desalination plants. If we follow the technology in Spain, which is the European country in which first the reverse osmosis technology was developed. As I said before, in 1964, the first desalination plant was built in Lanzarote. In 80s, they were built the desalination plants for irrigation. In the 19s, the construction of these plants was going on. Between 1995 to 2000, there were a significant growth in installed capacity. And in 2005, the AGUA program started. And now the current situation is more than 24 big desalination plants from the AGUA program working, and now we are starting to update these plants and to increase the production, expanding these installations. This is the situation now in Spain, more than 765 desalination plants between brackish and seawater. 99 of these plants are more than 10,000 cubic meters a day, 68 of seawater and 31 brackish water. The biggest one is in Torrevieja in Alicante, which is there, more or less here. The biggest is in Torrevieja. The capacity is 240,000 cubic meters a day, and this plant was built for drinking water, more or less the 60% of the production, and for 40% of this, its production is for irrigation. So as you can see, all the plants from the plant AGUA was built in the Mediterranean coast, in the East Mediterranean coast of Spain, and also in the Canary Islands. As we talk a little about the desalination costs in Spain, in the slide you can see the 7 desalination plants in the Murcia and Alicante area, from Alicante 1 to Torrevieja. You can see the capacity from 65,000 cubic meters a day to 240s, as I told before, the investment cost, and the total cost are between 0.66 euros per cubic meter to 0.68 euros per cubic meter. These costs that are highly dependent on the size of the plant and its workload. Some of them have some subsidized costs, and the range is between 0.66 to 8.68, as I said before. In the picture on the left side of the slide, you can see the picture of the Torrevieja seawater desalination plant. And if we talk about the desalination in the world, at this moment, the predominant desalination technology is reverse osmosis. The Middle East countries traditionally built a very big thermally desalination plant, multi-flux distillation, multi-flux desalination, multi-stage desalination plants. But since 5-6 years ago, they are changing the technology to reverse osmosis, and this boosts the reverse osmosis market. As for this reason, Middle East led the reverse osmosis production, led by Saudi Arabia. Spain remains as the largest market in Europe. And in the world, there are more or less 18,000 desalination plants with a CapEx of 5.8 million US dollars, and in OPEX around 8.2 million US dollars. So as you can see in the slide, the membrane technology are the predominant in the market. The thermal technology is still working on, but all the new projects are focused on reverse osmosis. They were awarded from the mid-19s. They were to 2024, where they were awarded around 110 million cubic meters a day in the world. And maybe the main issue is that and the last projects are huge capacity projects. So at the beginning of the 2000s, this century, the biggest projects will be around 100,000 cubic meters a day to 240,000 cubic meters a day, las in Torrevieja. But now we are building, they are building plants of 900,000 cubic meters a day, 900,000 cubic meters a day, or 800,000. So very big projects. Now the last big project is in Casablanca, in Morocco, in which Acciona is going to build an 830,000 cubic meters a day seawater reverse osmosis plant. Well, we analyze the annual contracted seawater desalination capacity by region in the last 10 years. Sorry, last 20 years. We have the Gulf countries are the biggest market, as I said before. The MENA countries, excluding Gulf, become a good market in the last 2-3 years, led by Morocco at this moment. And if we analyze the cost of the MENA projects in price and specific energy consumption, we can see a great evolution in water price. So we come from 1.2, 1.3 dollars per cubic meters in the early century, at the prices in 2024 of Sayedayat in Saudi Arabia, around 0.72 dollars per cubic meter, or Casablanca, about 0.46 euros cubic meter. Relating to energy consumption, at the beginning of the century, we have prices, energy consumption of about 4.8 or 4.9 kilowatts hour per cubic meter. and now we are energy consumptions around 3.2, 3.3 kilowatts hour per cubic meter. Slide shows the 20 suppliers awarded by desalination capacity. You can see the Spanish companies, Acciona, Bengoa, Aqualia, are in between all these companies. What about innovation trends? This moment, the innovation in reverse osmosis, well, in desalination in general and reverse osmosis focus on produce higher flux membranes and with higher recovery rates. Of course, the economies of scale play an important role. So for get these prices is only possible if we build a very big desalination plants. Also, new processes configuration can help to minimize the costs. Application of renewable energies, addressing biofouling, brine concentration, minerals recoveries, and digital innovation. So this is one of the focus of in which all the companies are working on. All of this, and digital innovation is also going to play an important role in the next future. And I think this is all. Thank you very much for your attention, and I'm open for your questions. Thank you.
Thank you, Jorge. We have a couple of questions. So the first question is from Bart. He's asking, how does your multi-stage RO compare to the second two-stage biturbo concept proposed by FEDCO? Did you notice some advantages with respect on fouling, in particular biofouling? And finally, what is your reference energy consumption, as you are speaking of a 0.2 kilowatt hour reduction in energy consumption? Luca, I believe this question is addressed to you, or Jorge, you can also answer this.
The first is what is the biofouling in multi-stage distillation processes?
So the question is, how does your multi-stage RO compare to the two-stage biturbo concept proposed by FEDCO? This is the first question.
I think this was
Okay,
related to the INDESAL scheme.
Yeah. We are now at, well, maybe Luca can answer better than me. This doesn't, but I think, well, in my opinion, we are testing now this concept. So we are now with the first results at this moment, no, Luca?
Yeah, but I think basically the main difference with the FEDCO design, let's say, is that in our case we don't use the multi-stage design to increase the water recovery, but it's mostly to achieve a better performance in terms of energy consumption. So it's not like a conventional multi-stage as the one is proposed by FEDCO, but it's slightly different. Also, the main goal, let's say, is different. And when we go to the part of the fouling and the biofouling, we didn't get any proper insights with this regard so far. But this is in part is part of the question because we have like 1 year operating, and we didn't observe any significant fouling problems. So to the pilot so far. So once we will complete the experimentation period, we of course also plan to do membrane autopsies in order to evaluate the extent of fouling and biofouling in the different membrane modules. And then I think there was the last and third one, which is like a complex question, this one from Bart, I think. The third part of the question was related to the energy consumption reference. And when we said 0.2 kilowatt hours per cubic meter of reduction, we compare it to a conventional desalination plant with a two-pass system, because we have a two-pass as well. And we, of course, compare it with the same recovery ratio and with the same influence capacity. So it's like a direct comparison for like the same process. The only difference is the design. I hope it answers.
Thank you, Luca. Now we have a question to Jorge. In your opinion, what has been the most important technical evolution in the RO?
It's difficult to say. There's not only one. There is different changes in all those years. So the membranes evolution, the evolution of membranes are one of the main. In mid last century, in standard conditions, 8 inches elements produce around 620 liters per hour, and only 99.2.4 of salt rejection. And now we have modules that more than 2,000 liters hour and 99.88% of rejection. So that means that the energy consumption is reduced because we produce at the same pressure, we produce more water. And this was one of the main evolution. The other is the energy recovery devices. So all seawater desalination plants recover the energy coming from the rejection, coming from the concentrate, which is high pressurized, still high pressurized. So at the beginning, they were used Francis turbines for recover the energy. Later, the Pelton turbines become a standard in the technology, and most of the agua plant desalination plants are working with Pelton turbines, and now the technology energy recovery devices. Hyperbaric recovery devices. Yep, hyperbaric chambers that become the standard and are at this moment are the more efficient for energy recovery of the desalination plants. So I think these are the most important. Of course, also changes in the design of the plants, more efficient pretreatment. So the multi-factors can affect the evolution of the reverse osmosis plants.
Perfect. Thank you for this answer. We have another question. From Andrea, which brine-based volume ration do you need to use in EDBM for achieving such high molar concentration in the product 3M? And the second question is, which level of divalentication concentration did you test, and which problems did you encounter apart from the performance reduction, scaling, membrane damaging, etc.?
Thanks. I think I will ask to the University of Cantabria representatives if they want to jump in order also to, because they are the partner in charge of this technology. So maybe they can give better insights with this regard. I think there is Marina.
Well, regarding the first question refers to the brine to base ratio, volume ratio that we are using to achieve a high concentration of the products, I think. In the test that we have performed in the laboratory, we were using a volume of 1 liter for the base and the acid solution, and with the brine we use 25 liters. So the ratio to achieve this concentration was 25 to 1, 25 brine and 1 in the base and the acid solution. But this was made like this in order to approximate to the pilot plant configuration, where we have a continuous flow of the brine passing through the module. So we have a constant concentration of sodium chloride. And regarding the level of the divalent cation concentration, we, as Lucas said before in the presentation, we installed a nanofiltration pretreatment in order to reduce the concentration of these divalent ions, and because it will affect to the process. So with this nanofiltration pretreatment, we achieved a concentration more or less of 230 ppms of magnesium and 400, 300 something of calcium, ppms of calcium. This means that we reduce an 80% in the content of magnesium with the nanofiltration and approximately 66% of reduction of the calcium concentration to the brine. Of the brine. So we have a considerable reduction in the divalent cations. And regarding the problems or yes, that we can find with this divalent concentration, of course, the scaling or the membrane damage, but also at pH 10, more or less 10, pH 11, this the calcium and magnesium hydroxide can precipitate, so it can form some precipitation in the base compartment. So it will lead to an increase in the pressure or a decrease in the flow rate of the base. But this is why we perform cleanings after each process, so we can avoid these problems. Also, another problem that we can encounter is that these precipitations or these divalent ions also increase the voltage or the resistance of the module, so the voltage increases when we apply the same current. So we have a little bit more energy consumption when having divalent ions.
Thank you, Marina.
You're welcome.
And now I would like to pass the floor to our next speaker, Professor Jose Luis Cortina Payas.
Thanks, and thanks for all the audience. My topic today is going to be covering what is the state of the use of the electrodialysis bipolar membranes for a production of chemicals from brines. I was reviewing that maybe in the last we are like prisoners, or maybe it's because we love brine valorisation. For example, here we have this new project that is a Marie Curie program for PhD students. But I remember that the first project that we were doing on valorization of brines was back to the year 2008, where we were evaluating the possibility for a chloroalkali company to use the brines from a RO facility just to be used as a source of sodium chloride for the chloroalkali industry. At this stage, I mean, the technology for reusing or not use brines from RO desalination plant, but just delete from seawater, it was developed in the 60s or the 70s. In Japan, as they are not having access to rock salt, they develop the use of the electrodialysis to have you here in the right when you are getting seawater with 3.5 grams per content of sodium chloride, and you need to concentrate more or less to 25%, and after that, you should not continue concentrating by ED, and then you should go to mechanical vapor compression to produce salt that could be used for table salt production or other uses. And we demonstrated here using the desalination RO that the target objective to be this commercial, you need to achieve brines a concentration factor to have, let's say 25% of sodium chloride with electrical consumption for this stage of less than maybe 150 kilowatts hour per ton of sodium chloride that is transported. But, this technology was destroyed by Rio Tinto because they started producing salt in the northwest of Australia by using natural evaporation. And that was really not the good news for the industry or especially for the producers of ion exchange membranes, because the market decreases exponentially. But we have very, very good news, because in the last years, the pressure driving technologies, high pressure, ultra high pressure RO, osmotically assisted RO, salinity rejection RO, for high pressure NF, has demonstrated that here on the middle stage, we have the desalination plant, and then we need to concentrate again this sodium chloride, not in the case of seawater. Maybe you are starting at 7% sodium chloride, just to reach after, if you want to produce a very, very high quality sodium chloride to be used, for example, in the chloroalkali industry, to use mechanical vapor compression to get sodium chloride with the purity that is acceptable for the chloroalkali industry. And even I think there is a full-scale applications in Indonesia using osmotically assisted RO developed by high-tech technology, and we are going to pilot inside the EIT raw materials program, piloting project here in Spain, in the south of Barcelona, in Tarragona, for the production of salt vacuum to be used for industry that is producing chlorine, and also to recover magnesium hydroxide. In that case, the business case will be a desalination plant that is going to be producing, let's say, around 6 million cubic meters of fresh water per year. And this will provide the possibility to recover 200,000 tons of sodium chloride and close to 9 to 10,000 tons of magnesium hydroxide per year. But the question is, apart from using those technologies to produce sodium chloride, are membrane technologies suitable to produce other chemicals? And we have seen in the presentation of Luca that the production of chemical, neither base or base especially, is done typically by the chloroalkali industry when you are starting with sodium chloride, and then you get as a byproduct chlorine, and also you are producing hydrogen, and then caustic solution around 30% if you are using membranes. If you are using the diaphragm technology, you are having, let's say, similar values, but the sodium hydroxide that is produced is more diluted. And there are two other possibilities: is to use bipolar membranes. In the case of the bipolar membrane, we have seen that the global reaction is different. We are not producing chlorine; we are producing oxygen in the anode and hydrogen in the cathode, and then thanks to the use of the bipolar membranes, we could produce sodium hydroxide and hydrochloric acid. And there is a big reduction of the energy requested because this reaction is only requesting 123 volts at 25 degrees. And also, even it's postulated, but there is still the technology is under development. You could use what is called direct electrodialysis, where also you are producing hydrogen, oxygen, and then hydrochloric acid and sodium hydroxide. But if we review what happens in the case of using bipolar ED, a bipolar membrane is just you stick together a cation and anion exchange membrane. And then in the interlayer between these two membranes, basically you are having water, and then you could not be using the energy you apply and different voltage to this system. The energy is not used for transporting ions, and then you reach this area where the energy that you are applying is just is used to do this reaction of ionic water splitting when you are transforming the water molecules into protons and hydroxide ions, and then transported through the cation and to the anion exchange membranes, and you could build if you want to produce acid and bases, like this three basic unit when you have the bipolar membrane, and then you need a cation exchange membrane and an anion exchange membranes just to produce, in that case, if you are using sodium chloride, sodium hydroxide, and hydrochloric acid. But this is very, very new. I will say no. You know, we already have one thesis by Monica Rech back to the more than 10 years, where we were demonstrating this of getting the brines from our RO, as it was a question and is very, very relevant. You need to remove calcium and magnesium levels if you want to avoid after problems, neither in the ED or in the EDVM or the EDVM stage, because the recommendation from some companies, you should not have more than 10 milligrams per liter of calcium and magnesium. But this is something that has not been fully demonstrated. I will recommend even just to have values of calcium and magnesium. Maybe should be below 1 milligram per liter. And when we were doing this project, we were facing that we were only being able to reach as a maximum, let's say 2 molar sodium hydroxide or 2 molar hydrochloric acid. This is only 4 to 8% in weight for those two solutions, far away of this 30% of the typical reagents that you could be you are commercial, or the chloroalkali industry is commercializing. And the fact is, when you are analyzing the amount of sodium hydroxide that you could produce from the brine that is generated in a desalination plant, the numbers of the use of chemicals, especially hydrochloric or sodium hydroxide in a desalination plant, is not really very, very high. And then, as we were not having a clear business case, I think this project died. And additionally, still we were facing one problem, that the electrical consumption to produce 1 kilogram of sodium hydroxide is around 2 kilowatts hour. And we were having values that were moving between close to 4 kilowatts hour by kilogram of sodium hydroxide. Some years later, it was published this paper that is highly cited, even they were not having any experimental data on either. But this group of people from MIT, they were supporting the possibility of producing sodium hydroxide by direct electrosynthesis from sodium chloride. And the fact is that when you compare what are the limitations, and then let's go into make a comparison of the theoretical and the practical energy consumption when we are using all these 4 possibilities, just estimating what is the energy required. Here we have a summary where we have that, as described it previously, the theoretical in green is less than 2 kilowatts hour per kilogram of sodium hydroxide, is the value that the industry is reaching. These values we have seen before of around 2 kilowatts hour per kilogram of sodium hydroxide. When you to the bipolar ED, even the theoretical value that is predicted is lower than 1, the reality of the values that are reported in the literature, there are values even arriving to 3.6, that are the values that we were reporting in the thesis of Monica Rech, and there are no data related to the use of direct electrosynthesis. Okay, then I will show you what are the efforts that maybe you could find in the last years to decrease this energy consumption, to make the product that you are generating, let's say, more marketable. And finally, one thing is that we need to reach, or as much as you approach to the values that the sodium hydroxide is produced by the chloralkali industry, much better or much easier to be just the possibility to put in the market. Okay, then I will explain, because I have not many time, two efforts that one was developed in our group last years by Tamara Leon, who was working in the use of ED bipolar from sodium chloride solutions. And then one possibility was to optimize the operation. Basically, is apart from optimizing or evaluating the possibility of increasing the current density, we were focusing in two things. You have to optimize the concentration of the sodium hydroxide, playing with the ratios of the volumes of your reservoirs in the ED stack from the salt and from the base that it produced. And finally, the possibility to use feed and bleed configuration, and more especially, as much if you are able to increase as maximum as you could the sodium chloride that you are using in your starting solution. Then we were able to reach close to 5.5 molar sodium hydroxide. That is close to 18% in weight of sodium hydroxide. Those are different examples as a function of this exercise or this experimental evaluation of the different ratios of the different containers or the use of the current density. But if we analyze the specific electrical consumption, we could see here that increasing the starting sodium chloride solution, we were working with close to saturated sodium chloride solution, even to 6 molar. We were able to reduce the values, you see, from initial values of 3.4 that we have in kilowatts hour by kilogram to close to 2.5. Then we were approaching, still we are not reaching this 2 or less than 2 that has been reported for the chloralkali industry. But I think it's a big progress if you increase the sodium chloride concentration as much as you could. But if you are doing, and we are reaching 18% content, that is the half maybe of the one that is produced by the chloralkali industry. But when you are doing that, you enter in a big problem because it's the mechanism, the transport mechanism that occurs in a ED or in a bipolar ED stack. There are many, and then apart from the typical electromigration and the electroosmosis and the water dissociation, when you start increasing the concentration, is the back diffusion, the donor exclusion mechanism is not working, and then you have a big problem with the proton leakage, and then protons are passing through the anion exchange membranes, and you have the problem of the OH leakage to the cation exchange membranes. And apart from that, you could have transport of cations or anions through the bipolar membranes to reach the containers. Okay, then, as this is something that is difficult to fight with against thermodynamics or the mass transfer phenomena, the last effort that for me is remarkable is this paper or this study that has been published last year by the Tang and Shu group, where the idea is to neutralize this proton or OH leakage. They call this is online neutralization scheme. I will not provide the details, but they are neutralizing both, neither the acid or the basic stream, but let's go into see the numbers they have published. Here are the efficiency and the current efficiency, and especially in the bottom one for the sodium hydroxide. you have in here the values of the energy consumption that is diminished to close to 2 kilowatts-hour by kilogram. And additionally to that, you know, there are reporting that the current efficiencies are really, really high, close to 94%. If you compare, they have made this exercise to compare all the results published in the literature in the last, let's say, more than 10 years. You know, there is more, probably this is one of the lowest values in electrical consumption, and is also one of the, it's a very, very good value in terms of current efficiency. Okay, what means that now we are now approaching this 2% of the kilowatts-hour, kilograms of kilowatts-hour ton, kilowatts-hour by ton kilo of kilograms of sodium hydroxide, and we were reaching 88%. 88% is like molar sodium hydroxide, and it's approaching to this 30% of that is the sodium hydroxide concentration that you could find in the chloralkali industry. Then, what is next? As a summary, I think we need from the membrane providers to improve the chemistry. They are using chemistries that are maybe from the 90s. The industries that are using ED bipolar, they are expecting to be working in, let's say, over 1,500 to 2,000 amperes per square meters. We need to reduce the proton leakage. We need to reduce the hydrogen leakage. We need to deal with the possibility of the problem of the divalent ions scaling that were mentioned in the previous presentation. I think it's helping that there are full scale, it's going to be very, very good, very, very soon, let's say, full scale application using ED bipolar. But for me, even most of the people that is working here are related to the seawater RO business. I think the most successful applications will be appearing linking to the mining industry, where the mining industry is using huge amount of sodium sulfate. Is considered the elephant problem. You have here one example of the Jadar project of Rio Tinto in Serbia. They will produce per year, let's say, close to 55 kilotons of lithium carbonate. And as a byproduct, they will produce 260 kilotons of sodium sulfate. You know, there is not market for this chemical, and then the only way to make this project reliable is to use ED bipolar to reuse the sulfuric acid in the leaching stage and to use the sodium hydroxide in the neutralization stage to produce neither lithium hydroxide or lithium carbonate. And I'm sorry because I think I spend more than time that I need, but thanks for your time and your listening.
Thank you, Jose Luis. Now we will move on to Frank Newman, Director of the Institute for Infrastructure, Environment, and Innovation.
Yes, I would like to thank very much the INDESAL team for inviting us. Very honored to be in this webinar with these very high-level speakers. Thank you very much. I've been asked to tell something about the history of osmotic power production and also experiences from the past, as well as a very short insight also into some relevant European policies. I see that the time has passed a bit. Do I still have my 10 minutes or yeah, just ask for the chair?
Yes, take your time, please.
Okay.
We'll just have a smaller coffee break.
Yeah, so we'll hope I'll not talk very far into your coffee break then. I will try to stay within around 10 minutes. From lab to market, as I said, it's not an easy journey. Our organization, Institute for Infrastructure, Environment, Innovation, has a long-term experience in upscaling process of innovation, particularly in 3 fields, notably renewable energies and brine valorization, maritime innovations, and the last item, but that's not so relevant for today, is drones for sustainable aviation, but also for environmental monitoring. And I'm speaking here today also on behalf of the Alliance of International Alliance of Brine Valorisation and Osmotic Power Production, where you can see here some logos of the contributors to this platform. As I said, indeed, the upscaling process from the lab to the market is not an easy one. There are a lot of challenges. In my presentation, I will briefly touch upon the lessons learned from some of the osmotic energy pilot projects, let's say in the past 10 or 15 years. Very briefly, I do not need to tell this audience, I think, but as IMIU, we've seen that particularly upscaling is not an easy trajectory. And although in a lot of descriptions of European grant programs and equity investment programs in renewables, we always see that they want bold plans and upscaling in 2 or 3 years. The reality is really different. We see in our experience that it's more 8 years, and maybe even a bit longer, to stay for the best results in commercial upscaling. Yeah, you see some other points here, but I will not go into them for time's sake. Maybe you can do that in case there are any questions. So maybe a very short tour of osmotic power plants running from 2009 to the current year, 2025. And this tour is not complete, certainly not. And it's not also so much quantified, as a lot of these startups and of course ventures do not always publish all the actual results. And maybe also a small word here, thank you to Valladolid University, because together with the University of Valladolid, we have started a European and global overview of osmotic power plants. And this study, as you will also see from this presentation, is not finished yet. It's kind of halfway because it's not easy to get the information. But I think still the information from this study in the end will be useful, because that's what we all also have seen in the experience of IMIU. Innovation for upscaling, it's very important to build upon the earlier lessons learned. So just a quick overview from lessons learned so far from osmotic power plants. Here you're looking at a photo of one of the first osmotic power plants in a natural environment in the world. The Statkraft plant, everybody knows it here, I think, who is working on osmotic power production. Yes, sorry for the photo. Of course, the clouds in the back, they do not come from the osmotic power plant. They come from another pilot site of Statkraft in Tofte, notably. The osmotic power plant is here in front, the red brick building. And yeah, this was one of the first osmotic power plants in the world. And some of you may have visited also. I think some of the people in this webinar visit this site. And although the development went well and fast, actually, the plant was built in 1.5 years. In the end, the results were not sufficient for commercial upscaling as considered by the board of Statkraft. And the main reason actually being in this plant is that the costs and the works for the pre-treatment were way too high to make the power production efficient. Not many details are known of this exactly, but everybody who visits this plant can see is that actually it had 2 floors, and the upper floor was completely taken up by the pre-treatment. So yeah, the pre-treatment cost for this plant was too high, and it was found also in this experience that in order for osmotic energy production to be commercially viable, this pre-treatment really should be simplified with much lower cost. A next tour of a plant that's also not existing anymore. The South Korea osmotic power plant, this was a hybrid plant using brine of a desalination plant as input for the salt water. And the fresh water was coming from the runoff of a wastewater treatment plant. And yeah, this project has stopped in 2016. Main experience here were also that at that time, it was a PRO system. The modules and membranes used were not sufficient yet for commercial application. An important result of this project was that the environmental performance was greatly improved of the desalination plant, because the brine was diluted in the end, so it was has less impact on the river in which this was discharged. At this moment, by the way, works are going on to have a follow-up of this project after quite a long pause, also during COVID, with several actors, and also where input will be used from the experience in labs in the Singapore institutions. And yeah, I cannot say much more about this, but because this is all still in development, the follow-up of this plant together with Korean and Singaporean actors. But I think something may be known about this in maybe the coming year. Another plant that is still functioning and functioning well is the salt power pilot plant. And in this plant, brine from a salt factory is being used as an input, and as fresh water, processed water from the salt site, production site, is used as an input. And here there were a lot of adaptations to the membranes and modules, and now actually the current pilot is quite large, going up to 100 kilowatt. At this moment also is further looked into commercial applications, notably also from salt caverns that are used for gas stockage, but this is still under development. And yeah, here you see a photo on the right side of the pilot plant, which is housed in 1 or 2 containers. And then I will not talk very long about this project, but it's a very important project also for Life INDESAL, because Life INDESAL is also basically building upon some of the experiences of the partners involved in the REA-Power project. I think one of the key projects actually in the development of osmotic power production combining with brine valorisation. I think Professor Cipollina is a speaker later in this webinar, so he maybe even tell more about the background of this project. Important outcomes of this project, which was actually led to a lot of academic publications as well, was first that it is very good to use brine and salt bittern, so the runoff of traditional salt production sites, as you see here on the photo on the right in Sicily. As an input for the salt water stream for osmotic power production, much more efficient than using natural seawater. A second important point of this project was that it led to a great inspiration of brine valorization, maybe simultaneously with osmotic power production, distilling and extracting critical raw materials like magnesium and rubidium. And this project led to a lot of follow-ups and new European projects. Then a third item here was that the salt production can also be combined with brine valorization. And there were a lot of follow-up of this project, which I will not mention now, but I think probably also Professor Cipollina will go into this. And of course, also the Life INDESAL project is also for a part based upon the experiences in this project, because some of the actors and partners are the same. Another plant that is still functioning, the Red Stack site. Everybody knows it, I think, here, all the speakers. It opened in 2014. And here you see that clearly it takes also a lot of effort and rigor to upscale. I think one of the most important learning experience from this project was that it's perfectly possible to site osmotic power production in very highly protected natural sites. Of course, everybody in this audience, I think, and also the speakers will know this Natura 2000, a European ecological network, which has a very high legal protection of protected sites. It's not easy to get a permit to carry out activities, commercial activities in these sites, but that worked out here at this site. So I think Red Stack has very well succeeded in developing mitigation measures which enable osmotic power production in such a protected site. And maybe for the ones who are not have not visited this site or do not know it very well, just for your information, the blue building on the left side is actually on the freshwater side of the IJsselmeer Lake, a large freshwater body in the Netherlands. And on the right side, you see the site pointing in the Wadden Sea, not only a Natura 2000, but also a protected UNESCO site, actually, a natural site. And that's where the saltwater intake is happening. And yeah, you also see here that it was a challenging site because actually the pipelines, they go over one of the most busy routes in the north of the Netherlands. And at the same time, it's based on a protected sea defense. So it was not even possible to drill or to put the pipelines under the ground because it was not allowed to do these kind of interventions in its protected sea defense. So actually the piping here is just lying on the ground. And this site now, a grant was obtained last year from regional authorities to further upscale the amount of kilowatts generated at this site. And it led also to a lot of inspiration for later brine valorisation projects. And as a very good add-on, it was found also by the Red Stack that the stacks used for developing osmotic power production could be also perfectly used for other type of applications with other membranes. For example, CO2 capture and more efficient desalination with an RED system. Now to some of the newest plants worldwide. Here you look at the Switch energy plant in the south of France, where on the one side, the Rhône River is used for the freshwater input. And on the other side, there is the Mediterranean seawater as the saltwater component. And yeah, this pilot site has been started to build last year, November. And I think already first electricity was generated from it. So everybody is looking curious in this site. And what's also very important is like Red Stack, it's also based in a Natura 2000 site. So this also demonstrates that osmotic power production can be perfectly sited in a protected natural site. And yeah, that's then the newest. As you would say in Holland, hot from the needle is the pilot site of osmotic power production using the RED system in Colombia, in Barranquilla. And this site has been started building, was started in their development in November 2024. And is supposed to be finished in the coming months. And this is the first time actually outside of Europe in Latin America, there is an osmotic energy pilot site. On 3 June, there will be a meeting in Brussels, by the way, where some of the developers and the main designers of this site will be present. And this site, also important maybe to know, I don't have a nice picture of it, but the fresh water comes from the Magdalena River, which contains actually a lot of sediments. And the salt water comes here from the Pacific. So yeah, quite challenging location. Maybe now back to what we've seen in the accumulated experience with the osmotic energy pilot sites so far is some challenges are still remaining. I think the audience here, the speakers will know it, but I'm just listing them here. Of course, from the lab to the market, it's not easy because it doesn't mean only to produce something on a couple of square meters, but it enhances to produce something in a very large terrain. And actually also in order to for example, produce half a megawatt or a megawatt, millions of liters of water needs to pass fast modules and membrane systems. So that's still very challenging. So far worldwide, as we know, there is not a 1 megawatt site yet. But of course, this is the next step for some of the pilot sites that are running now on our plant. Second point is, of course, what is very important that we see also in experiences with from some of the developers that I've showed is that the one water is not the other water. The seawater of the Mediterranean has a very different composition than the water of the North Sea and of the river, for example. So yeah, each time it's not possible to have just one ready-made solutions for all water. So each time osmotic power production sites, they need to adapt their systems and tune their systems to the composition of the water that is present. So that will be a challenge, and that is some item that needs to be further developed. Just as an illustrative here, you see some differences between the Mediterranean and the Wadden Sea. But of course, this is also true for example, differences between the Pacific and the Mediterranean. So each time, very important for osmotic power plants, the systems, the modules and the membranes and the whole water management system needs to be tuned to the composition of the waters. As mentioned here one more time, also the other challenges but that are being conquered right now, of course, is efficient water pretreatment. I think that the current state of the art here is a lot better than it was in 2009. So the developers really have found smart solutions to this point, water pretreatment. I think both RedStack as well as, for example, Switch Energy, they have found good solutions for water pretreatment, apparently. Yeah, I've been also asked to say something very briefly about European policies. I will not talk very long on this. Don't want to bore here the audience. Maybe you see them all here. What's very important is that the lights of regulation and policy are at the moment on very high and bright green for both brine valorisation as well as osmotic power production. I will not go into all of them here, but maybe important is that osmotic energy production is recognized at the EU level as an innovative renewable. That was recognized in the adaptation of the Renewable Energy Directive, the RED III, as you see in the picture here. But I think the more important ones here are the Critical Raw Materials Act, which facilitates, for example, brine valorization a lot, particularly critical raw materials like rubidium, magnesium, but also others. And most important, I think, for developers and startups, as well as also other parties here, is the Net Zero Industry Act. Yeah, it was actually implemented already last year in force. And now also a plan, a more detailed plan for the Commission has become available on 26 February. Important points here are that this act is supposed to facilitate or more government spending on renewable power, innovative renewable power production in the member states. So more state aid, which is possible for the production of and upscaling of renewables, production of renewables. Permit time should be reduced to 12 months. That's a little bit ambitious from this act because every member state, of course, has its own regulation. But it also provides a good push that permitting should be promoted. And maybe important to mention here that these 12 months, that is valid for capacities under 1 gigawatt. So most of the osmotic energy power production plants, it's well under this half megawatt. So 12 months should be the maximum time of permit. There's developed of net zero acceleration valleys, and this is also something that member states should carry out. But in these valleys, several companies and industries can be placed, and also a promotion, fiscal and financial promotion mechanisms should be in place to accelerate the deployment of renewables, including osmotic energy production, which is also recognized together with brine valorization as technologies that fall under this Net Zero Industry Act. Yeah, that's also mentioned here as the last point. I will not talk. I've talked long enough now, I think. So here are some upcoming events at the Alliance. 3 June, we have a meeting in Brussels on osmotic energy and brine valorization in Latin America, and particularly also focusing on the power plant initiative that I showed. 12 June, we have an online kind of overview event during European Sustainable Energy Week. And there will be also a site visit plan to the RedStack site, but we don't have a date yet. We are waiting there for European actors to come and give us the final date of this site visit. Thanks to my team here for putting together this presentation. This is a little bit more than the team in the photo. In the photo you see here our site visit together with University of Palermo and some of the other partners, where we were visiting the Trapani project site of one of the European projects of University of Palermo. Thank you.
Thank you, Frank. We have just a bit of time for one or two questions, and we'll quickly go to a coffee break and continue. A coffee break of just 5 minutes. So the question is from Alba Lopez. Question for Professor Cortina. What could be the main limitations for building a large EDBM installation?
Okay. I could say that to our knowledge, there is not already, let's say, a large full-scale facility using ED bipolars. I think it's going to be very, very soon, maybe one, but I could not provide this information. But for me, the main problems are the following. There is a limited numbers of companies that are producing bipolar membranes. And then when you are starting requesting hundreds of thousands of square meters, I mean, it's availability of companies with the capacity for producing those membranes. Also, typically, because I think in the chat was a question, is typically those stacks are working at high temperatures, and for example, the membranes that are used in the chloroalkali industry are different, but could reach, let's say, 90 degrees. But most of the big bipolar ED membranes that are in the market, they could not be over 55 degrees, and then to be resistant to temperature is, I think, is going to be a challenge. And then the third one maybe is the fact that especially when expecting to be operating with highly concentrated streams, the potential or the possibility of using these higher current densities. So let's say if you want reaching 1,500 amperes per square meter, this is for me the third challenge that all of them are mainly related to the companies that are producing ED bipolar membranes. I don't know if Alba is satisfied with the question, with the answer.
Thank you for your answer. And just one question for Frank Newman. Do you see more potential for saltworks or seawater applications?
Yeah, with saltworks. Yeah, okay, salt production. Yeah, that's hard to say because the thing is that there's not at this moment an upscaled plant for seawater. It depends on a lot of things also. Like, for example, in very remote places where there's the right configuration of seawater and freshwater in remote areas, it could be very useful to have this kind of energy because in relation to wind and sun, which are variable, this is of course a constant form of energy. So yeah, it's very much dependent upon the site, I would say. Of course, what is very important is that for industrial applications, so to have brine from saltworks, that's a very high potential, and it makes the installation more efficient for power production. And of course, then you need a salt production site, and of course, not everywhere in the world is a salt production site. What's very important is also maybe to realize that there's also the specific site has implications for the costs. Like, for example, like in Colombia, where you have this also it's a kind of harbor, a wall in the middle of the freshwater on one side and seawater on the other side. The costs for such an installation, they go down a lot because you have a natural configuration that makes your installation cheaper. And the same is true, of course, if there is a salt production site with a enormous, of a good production of bittern. Yeah, it's commercially very viable. So it depends a lot on the location. So some studies of IRENA, the International Renewable Energy, have shown that depending upon the configuration, the capital investment costs can go down like 40% of ocean energies if it's just the right configuration. So I would say that's dependent upon where the energy is needed And how far would it be from the source? Yeah, so there's not a uniform answer possible. But anywhere where there are a lot of desalination plants or planned, like for example in the Mediterranean, and there is some availability of fresh water in a wastewater treatment, there's a high potential for power production. And the same is true for when the technology for power production from sea and freshwater would be improved, and also the local configuration of, for example, a sea defense or a port or anything is usable, then yeah, why not have osmotic power production site there? So yeah, I would leave the question kind of open, depending upon the site and depending upon the needs of the region, because it's not like how you call it? It's not like something that you can put anywhere. It's very much dependent upon the specificities of a local site.
We'll continue with Ramona Simon, Scientific Project Manager at the GEMA.
Oh, thank you very much. Thank you very much for the invitation to the INDESAL workshop today. So I'm Ramona Simon. I'm working for the GEMA, a scientific organization which is working on bringing science and industry together. And we were partners at the C4Value project. And here we initiated a SEN workshop agreement. And today I'm going to tell you what we have done in this context and what this document is about. So first of all, I have to go to the next slide. I'm going to tell you what is C4Value. So C4Value is an Horizon 2020 project where the goal was to apply a circular supply model from raw materials which are recovered from seawater brines. So here in this figure, you can see that we are using the brines from desalination plants, and here we developed in C4Value 10 different technologies for the recovering of minerals and metals. What is the impact of that? Of course, we have a new raw material source. By that way, we lower in the environmental impact, and at the same time, we also increase the water recovery, so that more water can be produced from the desalination plant. So a clear win-win situation. The project was conducted by 16 different partners coming from all over Europe. So you can find them here. The project was coordinated by Eurecat from Barcelona, and the timeline of the project, we started in June 2020, and in the end of November last year, the project ended. So what have we done in C4Value? The skipping is not working that good. So what have we done in C4Value? We developed 10 technologies. You can sort them into 3 main blocks. So the first technologies were about the pre-treatment of the brine. Then afterwards, technologies were developed for the concentration of the brine. And then technologies for the selective recovery were developed and further improved. This was done in the first time of the project, and afterwards there was the question, how can we all combine those technologies? And there was we set up a moving lab to demonstrate the process, also working with real brine. The moving lab was on the site of a desalination plant on Tenerife in Adeje, and there all the technologies then were tested in a process. And besides the technological developments, we also had a lot of assessments, exploitations, and further insights in the project. So we have done, for example, a market analysis and market requirement analysis to see in which sectors could the minerals and metals recovered be used, so that we can have a closer look into the market insights. We also did a sustainability assessment for the technologies and the process to see what are the ecological, the economic, and social impacts of the process. We also did a lot of communication and engagement with stakeholders, so that when we are developing the process, we also get a lot of feedback from the existing environments. And moreover, to get better insights into the minerals, metals which are concentrated in brines. And if there are differences, we set up a database, the seawater catalog. So there you can find over 150 samples were collected, and you find the different brine concentrations of different minerals in the sea. And today we are talking about the SEN workshop agreement, which was initiated by us, and I was very happy to chair this agreement. And of course, maybe some of you are asking, what is a SEN workshop agreement? And therefore, I'm going to show you what we have done. So we have done a research project. We gained a lot of knowledge from all these processes that has been developed, but also from the sustainability assessment and the market insights. And our goal was then to transfer it, to transfer our results into the future, because in C4Value, the target was to recover a lot of critical minerals and metals, which are in future needed in many different key technologies, which will support us to facilitate the green transition. So you see the C4Value minerals and metals can be used in batteries. We will use them in fuel cells. The whole renewable energy sector will use C4Value minerals and metals, and therefore we have to somehow create the transfer from the research project to the future. And a SEN workshop is let me say, a soft standardization measure, which can help to bring the transfer from innovation into practice. So the goal was to create uniform rules, also to create an general language about brine valorization. And the great thing also about SEN workshops is that first in, first defined. So we really could make the first standardization approach to brine valorization. And our goal was to create more acceptance in the markets. So what is a SEN workshop? So first of all, it's not a single workshop. The term workshop is a little bit confusing, but the SEN, this is the organization of all national standardization bodies of the European Union and the EFTA countries and Croatia. Here on the right, you see how this institution is built up. So you have the SEN, where all the national bodies are part in. It's on the European level, and on the world level, you have the ISO, also quite known. And on the national level, so we worked in this case together with UNI, the national standardization body of Italy. And this is how it's built up, and there's only one SEN in Europe. So what then is a SEN workshop? A SEN workshop represents the consensus of all the involved stakeholders, and this is written down in one deliverable in one document. And the process is organized that everybody who is interested can join this consensus process, and it's a public process. So you announce the document, and then everybody who's interested can join, and then you are this community who builds up this document. As I said, it's not a full standard, but at the same time, it shouldn't conflict with standards, because if you're making a standard, then of course there should be only one in this direction. The SEN workshop document is a recommendation only document. So you can take the advice and profit from that. How long is it valid? So it's valid for 3 years. And afterwards, the document can be extended or it can be transformed, for example, to another deliverable. So we can, for example, go from the recommendation only. We can go, for example, for European norm, but this will be checked after 3 years how the path should go. Yeah. So this is in brief what the Zen workshop agreement is about, and we were very glad that we had in C4Value the opportunity to put all our knowledge inside. So how did we proceed? We started in the C4Value consortium to think about what kind of topics could be very interested, what advice can we give. Then we were working with Uni as a secretary. We then wrote a proposal. The proposal was published, and then we could collect comments. And afterwards, we started with our kickoff meeting. And then we went into the elaboration phase. So this is how this procedure goes on. And in our case, we had 53 experts who were working in this document, who were then later for 8 months. So we were working on that on 8 months. We had a lot of meetings for that. And after those 8 months, we found a consensus to all the things which are inside the document. And in November 24, we published the document. It's now it's an open access document and has a lot of pages, 57 pages today. So yeah, and now the question, what is inside this document? So I'm go now to represent the consensus that we found from all those 53 experts. So the structure of the document was that we have the formal part, where very important the terms and definition part, where we defined a lot of terms around brine valorisation. In the next part, we were asking the question, what and why do we need brine valorisation? What could be drivers and what should be, fundamentally be there so that we can do it? In the next part, this is the technical part, there we describe the core process steps and how you can do a pre-treatment, how you can do the recovery, and there are different technologies described. And in the next part, we give advice and recommendation on good practice approaches. So that you have an orientation if you're starting a new big project, what kind of points maybe you should consider. And at the end, we were not just looking on the process, but we also were looking on the products which are coming out from the brine valorization and how we can enable market entry and what should we obey when we are doing this. So as you see, 57 pages is very long, so I try just to pick out some insights of the document. And we would start then with the fundamental prerequisites. So what are the conditions to do brine mining? And here we found that, of course, you should have a sufficient high concentration of the minerals and metals so that it's worth. And you should always check if it's economic viable. So, for example, the cost should be outweighed by the revenue that you get from the minerals and metals. You should also consider what kind of extraction technology you need, the energy sources that you use and the energy costs. And of course, you have to know the market prices of the minerals, metals you are going to sell. And at the same time, you also need to know what quality of raw materials you can deliver for the market. Another fundamental condition that should be there is that you should be compatible with the existing infrastructure. And you also should look what kind of infrastructure is around your plant. So can I transport my raw materials, for example? Do I have a good water supply? Do I get electricity? And so on. And the other part is you also should look for risks, but what kind of risk could be potentially coming to you. And therefore, yeah, we recommend to have a comprehensive risk management, also to check if maybe the raw materials markets are fluctuating very strong, how you can deal with these uncertainties. Then one simple question, what kind of infrastructure do you need in your desalination plant? So of course, here were a lot of points which refer to, okay, we have to lift the brine up, we have to transport it on my location. Of course, I need to have space in my location. If it's a brownfield, a desalination plant. But of course, I also need some space to store the minerals and metals that we have. And yeah, no, I need a transport infrastructure to sell, for example, minerals and metals which don't have a high revenue. Then transport costs could also be a point that should be considered. If we are looking now into the technology process, so we defined what core process steps are there in brine valorization, and we said, okay, however my brine valorization step looks like, I always have those 4 points. And we have always a brine pretreatment, we have a concentration step, then we have the compound recovery, and if it's needed, we also have a compound purification. So these are the 4 steps that we have defined, which are elemental. And therefore, for those 2 steps, we have looked, okay, what kind of technologies, for example, can you use to recover critical raw materials? And as you see, we have a lot of technologies which were discussed also today, which can be used for that. So it's not a must, but the choice depends on what kind of minerals and metals you like to recover. In the next step, we were thinking about good practice approaches, and we said, okay, before we start planning, designing, or implementing or operating the brine valorization unit, you have to check again the economic and market factors. You also have to check if the technology you want to use, if they are efficient, if there are new technological innovations which could be already applied and could be beneficial. As I said, the logistics and infrastructure are something you need to consider, but also politics and environments, and of course, the risk that you take. And when it comes to planning, here you also have a lot of key factors which you should obey. So of course, you should check if the process as it is viable. You should check if do I build it now on a green field, or do I build my new brine valorization field on a brown field? You should identify the brine that you're using and the minerals and metals inside, so that you choose which minerals and metals you want to recover. If you want to recover just one or multiple minerals and metals, then at the same time, depending on in which country you are or region you are, what governance and regulations should come along, and so on. So these are all the recommendations that we are given, and we are giving much more. We also give on sustainability and what you should consider with when you are assessing it, and also of the minerals and metals. But I hope that I could show you a little bit of a glance what we did. And yeah, and I hope that you could help it. And yeah, I also want to thank all the people who were behind this process. So I want to thank the C4Value Consortium and, of course, the 53 experts who were engaged in the elaboration of this document. And yeah, I hope that you are interested to read a little bit more about it. And I put a QR code here so that you can download the document. And yeah, happy to answer questions.
Thank you, Ramona. We'll move now to Andrea Cipollina, and after that, we'll answer some questions that are left.
Thank you.
Thank you.
So,
Good morning. Good morning. So thank you for inviting me to present the results of our project, the SEArcularMINE project, which is about the extraction of raw materials from bitterns. Bitterns are a very peculiar type of brines coming from seawater through a series of evaporating basins where sea salt is generated as a first product. But saltworks also generates a brine, very concentrated brine, extremely rich in magnesium and other valuable elements. The goal of our project was to develop technologies aiming at the recovery of these materials. And some key facts on the project: it was closed last year. It was a 4-year project with a total budget of 6 million euros, coordinated by the University of Palermo with 12 partners coming from all around Europe. And I mean, I need to mention the partners they were from academic institutions, industries, small, medium enterprises. You can see all of them have contributed significantly to the success of the project. And the overall scheme which we have worked starts from saltworks, so the place where sea salt is produced, and where the bittern is generated. And from the bittern, we try to extract as many minerals as we could with a fully integrated cycle in which we started recovering magnesium, but then we also looked at the extraction of lithium, other trace elements. And what made the process fully circular is the in situ generation of reactants that were needed for the separating, for the selective separation units. As a final step, we also tested reverse electrodialysis as a mean to generate electricity from exhausted brines. And last but not least, we also looked at the integration of currently operating saltworks with desalination plants. But in this case, inverting a bit the concepts, so not how to use the brine from desalination plants, but how to further enhance the productivity of an existing saltworks by constructing and integrating with a new desalination plant the existing saltworks. I will be fast in describing the technologies. You may have seen it already in other occasions. So we focused on 3 core technologies, what we called the magnesium crystal granulometry controlled reactor, which is a patented technology aiming at the production of magnesium hydroxide with a finely controlled granulometry and high purity. The lithium membrane flow capacity ionization unit, which was developed by our colleagues from the University of Lisbon, Università Nova de Lisbona, based on the use of lithium selective membranes, and trace elements pH swing adsorption technology, which was developed by our colleagues at Barcelona, UPC, aiming at a very selective recovery of a number of trace elements. There are also a number of auxiliary technologies that could be adapted to operate with brines. First of all, evaporative or osmotic pre and post concentration units. But as I said, one of the most important units, as it was the core of the circularity, was the EDBM, the electrodialysis with bipolar membrane units, able to produce in situ the chemicals needed for the process, and reverse electrodialysis adopted for power generation from salinity gradient. Among the non-technical objectives, but also very important, we have characterized the potential of bittern exploitation in the whole Mediterranean basin. And this was performed by collecting about 30 samples from all around Europe and let's say also North Africa and closest. And let's say analyzing the composition and the content in each targeted mineral. The project lasted 4 years, which were very intense, going through very fundamental laboratory scale research up to the implementation of a full-scale pilot plant. And these pictures show all the units that constituted the integrated pilot plant. As you can see in the order, ultrafiltration, first pH swing adsorption unit to recover boron and germanium, the magnesium crystallizer, and the second unit to remove hardness from the effluent from the crystallizer, EDBM unit for the in situ generation of chemicals, and then smaller units for additional steps like MVC concentration, pH swing adsorption for trace elements recovery, lithium recovery, and reverse electrodialysis unit as a last step. These units were all fully integrated within a unique pilot plant that operated in Palermo at the premises of the University of Palermo with real solutions for a sustained period of about 4 months. We also ran long-run operations with continuous operation up to 70 hours of all units integrated each other. And some key facts, some key results in a nutshell. About magnesium recovery, the crystallizer was tested and proved to be able to produce about 100 kilograms per day of magnesium hydroxide, which is already a significant scale. With a process yield practically of 100%, all magnesium was recovered from the bitter, and a purity which was, most cases, above 99%. Concerning the trace elements separation, the pH swing adsorption technologies, all of them have been tested and proven. We could demonstrate that boron, strontium, rubidium, cesium were, for example, separated with a high selectivity. And we could also achieve a perfect control of hardness in the brine, reaching the EDBM, thanks to the pH swing adsorption unit, eliminating calcium and magnesium, which at the end of the treatment achieved concentration values of below 5 ppm. Concerning the in situ generation of reactants, in particular the alkaline reactants, we could achieve very good performances. We generated the solutions that we needed inside the process at a concentration which was typically between 0.5 and 1 molar, exactly as we needed it in our units, with specific energy consumptions well below 1.5 kilowatt-hour per kilogram of sodium hydroxide, and a full circularity potential for sodium hydroxide reuse inside the system itself. And last but not least, also the reverse electrodialysis unit was tested, first at the laboratory scale unit and then in a pilot scale setup, with interesting values of power density around 8 watt per square meter achieved in the lab scale unit, and lower, around 5 watt per square meter, but with a much higher conversion, which was around 30% in the pilot scale setup. These are some pictures that I like to show with a group of people operating the plant in Palermo, and then also in Trapani, where the plant was moved after the testing phase in Palermo at the premises of Resources, which is a spin-off company of the University of Palermo. And this is a real picture of the drum filter where the magnesium hydroxide cake was filtered and generated. If you want to see more information on the pilot plant installed at Resources premises, you can also go. There is a very informal YouTube video that makes a virtual tour of the plant. And to close, I want to show you which is the next plant. So the University of Palermo has been granted a new life project, which is smaller and more focused on the specific case study of magnesium hydroxide production from saltwork bitterns. The partners are local partners, University of Palermo Resources, and Maremag, which is an affiliated partner to Resources, and Sosal, Nuova Sima, which are two Italian companies, Hellenic Saltworks, that is a company in Greece, which will enable the let's say reproducibility case in another saltworks. And the goal will be basically to show at a larger scale and at a higher TRL that the technology can be implemented to produce in a new way magnesium hydroxide as an alternative to Russian and Chinese mines with no CO2 emission and fully powered with renewable energies in order to go closer to the market. And the main challenges we are targeting with these new projects are to basically eliminate the use of harmful and environmentally dangerous products in two markets for magnesium hydroxide, the flame retardants market and the environmental applications market, to substitute brominated flame retardants and calcium hydroxide in respectively the two markets, plus the production of alternative compounds like hydrochloric acid, sodium sulfates for different but very wide markets. The plan for implementation is to go from the 40 tons per year pilot plant realized within the SEArcularMINE project to a 100 tons per year plant in the first Maremag industrial plant in Trapani, in the saltworks of Trapani, a replication study of 50 tons per year capacity in Greece, in Kythros saltworks, and then looking after the Life project implementation at the real industrial scale-up with a target capacity of 15,000 tons per year. With that, I close my presentation and thank you all for the attention, and I'll be glad to answer your questions.
Thank you so much, Andrea. As we're extremely over time, we only have time for maybe a couple of questions, and then we'll move to the closing remarks. So the first question is to Ramona. The CWA document seems quite formal. Does it carry any mandatory requirements, or is it more of a recommendation?
Yes, the process is very formal. There's a long guidance to make it, but to use the document is not strictly mandatory. So it's a recommendation only document, and yeah, you can read it, get inspired, gain knowledge, and yeah, so it's not mandatory.
Thank you, Ramona. And then there's a question to Andrea. How did you get to this low energy consumptions for NaOH production, 1.5 kilowatt hour kilograms, which are the lowest reported, well below 2 kilowatt hour kilogram for chloralkali?
Yeah, actually, we even achieved lower values around 1 kilowatt hour per kilogram. But you have to keep in mind that the target concentration was much lower than the values shown before by the other speakers. It was between 0.5 and 1 molar, and this enables to achieve very high current efficiencies and, let's say, relatively low applied voltage, which results in a low energy consumption. And you may ask whether it makes sense to produce such low concentration chemicals. It does in the case where you use internally your chemicals. In that case, there is no need to push on the concentration because you often need then to dilute the solution for final use. And this is one of the many advantages of in situ generation of chemicals in fully integrated schemes.
Perfect. Thank you, Andrea. I think we have a question from Frank as well.
Yeah, two questions. Nice to see you, Andrea. And yeah, very quick question. Of course, we had a very nice site visit to the SEArcularMINE project last year, and we saw there also the installation for the extraction of rubidium. I don't know whether you can share that. What is your estimation of the the commercial upscaling for this extraction in the application that you use? And the second question, maybe you mentioned for the osmotic power production, you reached 8 watt per square meter, as I understand. What do you think is the main reason that it's a little, quite a bit of higher than is common for this kind of installation? What is the reason for the success? Yeah, so these 2 questions.
So about the first question, rubidium extraction, from the scientific point of view, it was a success, and Professor Cortina and his team did a great job in identifying selective, very selective sorbent materials, which worked very well. The selectivity was very high, it was demonstrated, but the initial concentration of rubidium in the bittern was extremely low, so that basically we haven't even saturated the column during these several weeks of operation in the pilot. So I don't know, I would not be able to say whether it makes sense commercially or not. I can only say that it is extremely challenging to make it viable due to the very low concentrations in the feed brine. While about the values of power density, there were, of course, possible thanks to the very high concentration of the brine that was treated, because we are talking about a brine concentration between 3 and 5 molar. And the other very important advantage was that since the bivalent cations were completely removed, calcium is naturally removed in saltworks, while magnesium was removed because we wanted to recover it. It was a, let's say, dominantly sodium chloride solution, which, as you know, makes it easier to reach such high values of power density.
Okay. Yeah, so the combination of magnesium extraction is quite good, actually. Yeah.
Yes, magnesium extraction and very high concentration. And we have tested several different membranes, and with more than one set of membranes, we could achieve such high values. But this was confirmed also in previous studies. As you mentioned, in the Repower project, we also deal with saltworks bitter, and after the magnesium removal step, we could also achieve such high values of power density.
Yeah, it's a potent solution. Thanks.
Thank you both. And now we'll move to our wrap-up of the session. I'd like to pass the floor to, to Jorge.
Hello. I don't have too much things to mention because we are very overpaced the time. But I would like to thank you, all the speakers, for being with us. I think it was a very interesting webinar in which we have the opportunity to cover the new developments for increasing or minimizing the impact of the reverse osmosis and minimizing the energy of the process. We have the opportunity to talk about the very important research topics in the present, like osmotic energy, like EDBM membranes. We have the opportunity also to know about the works involved in other European projects like saltworks and etc., in which we can see the potential of the brine valorization for recover salts from the seawater, and this is a very important topic in the last years because the Middle East market are leading this kind of issues relating the use of these raw materials. So thank you very much. I don't know, maybe we have a small time to answer some questions, remaining questions. I think I have a question for Andrea about the Spanish market. Andrea, I think
You have an
ask
answer?
about, figures on desalination in Spain are very encouraging for the other EU countries. I am positively surprised, especially by the low specific cost of water, which is the energy cost paid by operation for operation. So the energy costs in the big plants of the Spanish market are around 3.7 kilowatts hour per cubic meters to 2.9, depending on the size, depending on the technology, because you have to take into account that the plants were built between 2004 to 2007, more or less. So they are the technology for energy recovery devices, for instance, are Pelton turbine. So, but the last
Jorge, can I ask you? Sorry, the question was more on how much you pay per kilowatt hour of electricity, which is the cost of electricity, because in Italy it's extremely high, and that kills basically the economics of desalination.
I see, but the energy depends on the day, in daily basis, because it's highly depending of the composition of the pool of energy. That means if the energy is part of renewable or more renewable one day than another, of the energy is becomes from thermal combined cycles, or now it is possible to get energy from nuclear stations. So it's changing in daily basis. Yep. And the energy, the government funded a company called Aquamed, which is in charge of all the managing. He's the owner of the plants, so they bid the operation of the plants. So we are in charge of some of these plants from Aquamed, as well as other Spanish companies. So in most of them, the energy is paid by Aquamed. That means that by Spanish government. Yeah. In others, no. In others, no. But in some of them are paid by Aquamed. So we are not in charge of pay the energy. Yep. And the other question is of the 5 million cubic meters installed, which are the actual average daily production. So it depends. This 5 million cubic meters a day is not only the bigger plants. So this included plants for private plants, for hotels, for tourist resorts, so for a small agriculture's association, etc. So if we take into account the bigger plants, that means those that was built in the agua desalination plants, sorry. The production depends on the season. So from April to October, they always almost work at full capacity, because in villages like Torrevieja, the population increased 3 times from winter to summer, spring and summer. Yeah, so the plants works full capacity. The last 5 years, we have a very hard, severe drought situation in Spain. So all the plants work between 70 to 100% full year, almost full year. Okay. Now it's raining, so who knows what is going to happen this year, because the dams are not complete, but have a lot of water. So this is the situation at this moment, yeah, in Spain. Okay.
Thank you very much.
I hope I answer your questions.
Yeah. Yes.
Thank you both. I think we will need to wrap up, as we're already 30 minutes above the time limit. But Jose, I see you have your hand up. Maybe you want to also make a final remark?
No, it's a short comment to the question from Andrea. This is like a secret information, Andrea, the price that the companies are paying. But I could say that the last number that I got in February maybe it's like around 100 euros megawatt hour. Including everything. Okay, is in the market you have like previously it was around that Jorge was mentioning around 60 euros per megawatt hour, and then you need to add between 20 to 40. That is all the cost related to transportations, and then in February the price was around, let's say, 100 euros megawatt hour.
Well, thank you. Thank you, Jose Luis. And thank you everyone for joining the INDESAL webinar. I hope it was very insightful for everyone, as it was for all of us. As we already said, you will receive all the answers to the questions that were not unanswered via email, as well as the recording to the webinar, so you can share perhaps with your colleagues who weren't able to join the webinar today. Thank you to all of our speakers for joining us, for sharing all the results of their projects, and have a lovely rest of the day.